Good afternoon, everyone, and good morning to those located at the West Coast. Thanks for joining our webinar today. My name is Hai-Yin Chen. I'm in charge of our Technical Application and Support Group at Sepax Technologies. Sepax manufactures chromatographic products for large biomolecule separations. During many of our technical support sessions, we get questions on the protein separation, a lot of questions such as where to start and how to optimize the separation conditions. So we hope today's webinar will take away some of the difficulties and also shed some light on the method development for the large biomolecule separations. Our webinar will focus on the cation exchange method development, particularly for map separations. Here's our outline of the webinar today. We'll do a little intro into the map heterogeneity and then the little overview on the IEX chromatography theory, and then also we'll discuss the phase chemistry differences among the cation exchange columns we manufacture here at the Sepax. Then we'll move on to the monoclonal antibody separation method development. We'll talk about the variables going into the method development, such as the buffer pH and the salt and ionic strength, gradient, flow rate, and the resin particle size. Also, we'll move on to the column comparison. So there are quite a few columns on the market. We want to see what are the differences between our column and then the columns on the market. We'll do a case study doing the mobile phase and the column phase screening using different mobile phase and also the cation exchange phases we have at the Sepax. And then we'll talk about some applications on the monoclonal antibody separation using the optimized methods that we'll talk about in this section here. Then we'll move on to the conclusion. We'll do a Q&A session at the end of the webinar. For this webinar, we muted everyone, so if you have any questions, please do not hesitate to type into the question box along the presentation, so we'll answer those at the end of the presentation. All right, let's talk a little bit about monoclonal antibody. It is a very important class of therapeutic drugs. This graph taken from the report published by the Pharmaceutical Research and Manufacturers of America last year in September. As you can see, out of the 900 drugs in the clinical trial, a third of them are monoclonal antibodies. And they're really covering more than 20 therapeutic areas. The cancer and also infectious disease are the top two categories. Monoclonal antibody by nature is very heterogeneous. So that's one of the common features for MAP. So the analysis is really important for the quality of the drug design and the production and the getting to the final stage of the clinical trial. ICH has a guideline for the stability testing for the MAPs, with different forms of deamidation, oxidation, and aggregation. So the high-resolution chromatography is one of the techniques listed here for this testing. And among the high-resolution chromatography ion exchange, I highlight here we're going to talk about today. So we'll reserve the geofiltration for the sizing differences, another topic for another time. A little bit about a heterogeneity of a monoclonal antibody. Now, this is a very simple diagram where all the major heterogeneity located on the map structure. I want to point out this reference paper. It's a very good reference paper for you to read if you want to know what are the monoclonal antibody heterogeneity. And also in the paper, it has associated with all the known map heterogeneity published by the other researchers as well. So in summary, we can see here first the most common modifications on the recombinant monoclonal antibody, the C-lysine, terminal lysine processing. So with the mixture of 0, 1, and 2 on this heavy chain, the C-terminus, we can have a different charge variance with different lysine groups on the terminus here. The second common heterogeneity modification is the deamidation of the asparagine. The perfect composition, ionic strengths, and the pH can all affect the rate of the deamidation. Actually, deamidation can occur during any stage of the process. Deamidation of the asparagine can lead to isoelectric and aspartate group, so that introduces the more acidic species into the map. Another acidic species, more acidic species introduction is by the N-terminal heavy chain N-terminal pyroglutamate formation. A lot of times the heavy chain N-terminal has a glutamine or glutamate. So with glutamine, you can have the cyclize into pyroglutamate entirely or partially, so that introduces more of the acidic groups. So with both of these acidic groups introduction, these acidic species will elute on the cation exchange earlier than the other species. Another common modification is the disulfide shuffling. You can see we have 12 pairs of disulfide bond here. Sometimes they are incomplete disulfide formation, so that will lead to the disulfide shuffling. With disulfide shuffling, map can be changed structurally, so that will lead to the local surface charge different among the different disulfide species. And now also another one of the very common heterogeneity of the map is the glycosylation. On here we have two very conservative regions and glycosylation. So glycosylation can actually change map structurally, so that will lead to the charge variance as well. And also by itself, the glycosylation, sometimes you have a differentiation at this terminus of the glycosylation, so that will also give you different charge variance as well. So with all these different charge variants, it's really naturally you're thinking, ion exchange can be a perfect choice to analyze those variants. Before we get into the map variance study on the IEX, we'll talk about IEX in theory a little bit. So since IEX is all about the charge-based separation, we'll talk about protein surface net charges first. That's actually a foundation of the separation here. In this graph, we can see there are two hypothetical proteins with pi. One is at 6, the other one is at 8. When pH is equal to pi, you have the net charges at 0, so protein doesn't really bind to either of these phases. When you go the pH below its pi, you have more of the net positive charge. The protein can bind to the cation exchange. So cation exchange resin here has negatively charged functional groups. On the other side, if you have pH above the pi, so you have more of the negative charge, then the protein will bind to the anion exchange resin where all the functional groups are all the positive charge here. So a little summary from the previous slides. Protein net charges are buffer pH dependent. Net charges at 0 when the buffer pH is at pi value. You use a cation exchange if you use a pH lower than pi, so the protein has positive net charge. Use anion exchange when the pH is greater than pi, protein has negative net charge. Sorry. All right, this is a little animation showing you how the ion exchange works. You have 3 different charged proteins bind to the resin. When you apply the salt or a pH gradient, you have the protein start to elute with the least charged protein coming out first, and then the second, and then the most charged with the 3 charged group coming out the last. Here we talk about is cation exchange. As you can see, the resin supporter has negative charged functional groups. The column can be re-equilibrated for many runs. So at the end of the gradient, you will go back to this initial buffer condition and equilibrate the column, and then reload, re-inject another sample. So it can go many times. Some considerations for IEX separation. First, you have to consider whether the buffer pH and the ionic strength you choose is compatible with the protein stability and activity. So if the protein is the most stable below pi, use a cation exchange. If a protein is most stable above pi, use anion exchange. Some of the proteins are stable over a wide range of the pH. You can try either type of the IEX phases. In our map cases, a lot of examples we talk in this webinar, the maps have pi between 7 and 9. So cation exchange has really become a commonly used IEX phase for these variant studies. And then it can become a common platform for if you have a class of a monoclonal antibody. All right, let's move on to Sepax cation exchange phases. So we offer 3 cation exchange phases with Proteomix SCX and WCX, and then there's another one, AntibodixTM. The difference between the WCX and SCX are the functional groups. With WCX, the carboxylate as the functional group here is a pKa at a 4.75, and the SCX is a sulfonate group with pKa less than 1.0. I have to mention all 3 phases are PSDVB, the polymer-based resin core structure. So all the cores here is the same with the PSDVB. The difference between the 2 WCX, we have a Proteomix WCX and Antibodix WCX, is the linker chemistry. With Proteomix WCX has more technical linker for the Proteomix WCX, and then a random polymer linker for the Antibodix WCX. So it is more hydrophilic in the case of ABX WCX. Operational-wise, difference between WCX and SCX, because WCX has a higher pKa. So in order to charge all these functional groups, we'll need to have a pH above pKa. So for WCX, you have a little narrower working pH range. Ideally, you normally will do pH 5 to 10. And SCX, because the pKa is so low, you can widen your working pH range. For all 3 cation exchange phases, we offer 1.7 to 10 micron. So we do, all the examples actually here is a 5 and 10 micron. If you have more interest on the other particle size, we can talk a little bit more offline. The columns we offer for all 3 phases, stainless steel and also PEEK. I would recommend PEEK if you're working with a lot of biomolecules, because PEEK is a bio-inert material, so we'll give you less of the interaction during the process. Buffers for cation exchange chromatography. Here are the recommended buffers for the separation, because the ionic interaction between the samples and the resin functional groups depends on the pH. So maintaining pH when you're using the salt gradient is very important. Here we have a wide range. You can go as low as 1.4, it can go as high as 8.8. A lot of times, when you're running the native protein or map separations, the low pH range may not be applicable, because a lot of proteins are not stable at a very low pH. They tend to be degraded, or at a much higher pH, you get a deamidation happening. So when you want to run the native separation, you want to use the middle part here with all the buffer maintaining the pH for the separation. So when you don't know the property of the map and just want to see what works, so here are the 4 recommended common buffer system you can start with the pH 4.3 to 5.3, the acetate buffer, the mass buffer pH 5.6 and 6.6, and also the most common ones are also the phosphate buffer 6.7 and 7.7, and with the Hibis buffer at a higher pH. To start out, you can choose a buffer A concentration with 10 to 20 millimolar to start. And then the buffer B, you can just keep the buffer A and plus the 1 molar salts. You always can change the concentration of the salts in the B buffer depending on initial screening results. But I highly recommend that you have 1 molar salts, at least in one of the mobile phase, so you can clean your column after a few runs. For some of the samples are very sticky, then it's very recommended to use a higher salt to wash your column. For pH, at least 0.5 or 1 pH unit below the PI. Here we're talking about cation exchange. So these pH difference from the PI will be needed to elute the protein off. And as you can see later on with our map separations, we do have 1.5 or even 2 pH unit below the PI for the buffer system. You can change the gradient to see the effect on the elution and modify the parameters. We'll talk about those later. And also when you select column or do the columns, it's really important to pay attention to maintain a column lifetime. Pre-column filter, the guard column installations is really important to get rid of some particulates or some non-specific binding proteins. And to filter the buffers, no particulates left in the buffer, and also centrifuge the samples before injection. So these are the necessary steps to really extend the column lifetime. Now let's move on to the variables, go into the cation exchange map separation method development. We have a few parameters here you can make adjustment. The first, the pH of the buffers, we'll talk about that effect, and also, of course, the ionic strength of the starting buffers. Elution salts, the counter ion will make an impact on your separation as well. And a gradient adjustment, that's very common when you do the method development. Flow rate as well, so it can speed up your assays. And also the column temperature, that will have an effect on the separation, but you have to really be careful on the effect on the protein structure and the stability. All right, let's go one by one through these parameters and see some of the examples how these parameters impact on the separation. First, the buffer pH, so antibody-ionic strength effect on the cation exchange separation. As you probably remember, we talked about a titration curve. When you see the lower below the PI, reducing the pH, you have more of the net positive charges. So the map will bind to the column tighter, and then under the same program, you're going to elute later. Increasing the pH, you have less of the net positive charges, so the map will elute earlier. And also buffer A concentration has impact on the separation. Increasing starting buffer concentration, that will definitely also reducing the map binding, so elute earlier as well. Here's the first example with the pH dependent. We're using AntibodixTM 10 micron column here. The buffer system is a 10 millimole phosphate, and then with some salts in the B. pH we showing here is pH 7.5 and 7.0. As you can see, when we increase the pH from 7.0 to 7.5, the separation, elution of the map peaks coming out earlier, and also under this pH adjustment, we actually maintain the separation resolution here. So that really gives us the advantage for a shorter run. And also we can see the impact on the higher pH, so the map elutes earlier. Also the ionic strength of the starting buffer A, we have a map here with phosphate buffer at a pH 7.5. Also the 10 micron and WCX, we have 3 different starting buffer A concentration. And then we have with the 20 millimolar sodium phosphate, most of our peaks coming at the very beginning. And even though we do see some separation, but they really come out together. When we just reduce this buffer A concentration to 10 millimolar, we see so much more improvement on the resolution of these map peaks. When we reduce further to 5 millimolar, we still see the separation, but we start to see the loss of resolution, and it came out much later. And it's actually highly recommended not to go below 10 millimolar of the buffer A, the salt concentration, because it starts to lose the buffering capacity of for the system. So when you run the salt gradient, you want to have a consistent pH throughout your runs. So if it's not necessary, then maintain at least 10 millimolar salts in the buffer A. Here's the next example of the pH dependent. We have done quite a bit on this map. We're using actually the sodium acetate and lithium chloride gradient. We'll talk about the counter-ion lithium chloride a little bit later. Here, the effect we want to see is the pH difference here. At pH 4.9, we can see most of them out at the end of the gradient. And when we start to increase the pH, the maps start to come out earlier, and we do have much better resolution with the increase in pH. However, there's not like a never-ending adjustment. We can see at the pH 5.2, most of the map coming out in the flow through only a little bit got separated here. So the optimum pH here is a 5.15. We get a really good separation with this gradient. So pH adjustment will give you a really big impact on the separation. And in this case, pH is, the map separation is very sensitive to the pH adjustment. Okay, so we talk about the pH impact of this for the buffer system. Now we're going to talk about the elution salts. A lot of people, I mean, most of the cases, sodium chloride is fine. I mean, that's most common counter-ion to be used in the cation exchange. However, lithium chloride will give you a different selectivity because the different elution strengths. As you can see here, these are the four commonly used counter-ions in a cation exchange chromatography. And that's with the increasing elution strength. So lithium has a lower elution strength than the sodium chloride. That will give you an impact on the separation. And also we'll talk about salt concentration in the pH gradient. And you have the regular pH gradient, but what if you add some salts in there? So we'll see some of the results from this comparison. First, the lithium chloride and sodium chloride with a different the counter-ion in the buffer B. This is the separation we have seen before in the pH effect there. And it shows really good separation. But once we switch to sodium chloride in the B buffer, we can see most of the proteins came off in the flow through. We have a 10-minute isoelectric here. However, we did not optimize this gradient for the sodium chloride. I imagine if you change some of the ionic strengths, you may be able to improve the separation. However, we do get a really satisfactory separation with the sodium acetate and the lithium chloride gradient. This is a comparison between a pH gradient and pH and a salt gradient. And then this three-component pH gradient actually is coming from a paper published by Genentech researchers. They had done very extensive study on this three-component buffer system on a class of their map separations, and it worked really well. And then there's a lot of discussion go into the concentration dependence, things like that. We took a little easy way out. We borrowed the three buffer component buffer system and ran on our in-SCX and P5 column. Under this condition, without the sodium chloride, we actually do get some separations, but it came out pretty late in the gradient. We did not further optimize this purely pH gradient, but I think you can do improve the separation here. But however, on the other hand, we have another buffer system. We add a half molar salts in there and then ran on the same column. We did get a better resolution with the salts added into the pH gradient. So it does have the impact on the separation. The peaks coming out earlier, I think it's due to we increase ionic strength in the B buffer. We start out 5% because the 5% have also a half molar salts in the B, so we do have a higher ionic strength, so the proteins start to come out earlier. So we can see the effect with and without salts on the separation of this particular map and under this particular buffer system. Okay, so we talked about the pH of the buffer system and also talk about ionic strength, and now we're going to move on to the gradient. Really the general thinking is the slower the gradient, the lower the protein will elute, and then also you'll get a better resolution. That's what we're hoping. So and then let's see what kind of effect have on the separation with some of the examples we present here. This is the AntibodixTM MP10. It's a 10 micron column with 10 millimolar phosphate buffer concentration, initial buffer concentration. It's a salt gradient. We start out with a 15 to 75% B in 30 minutes. It comes up actually, you know, it's pretty nice already. But once you slow down the gradients, which means you narrow your the B concentration in the same time frame, you can see the protein or the peaks start to pull apart even further. However, to a point, when you slow down the gradient, you also dilute your peak fractions as well. So to some certain degree, you know, once you get diluted too low, you're not going to be able to see the peaks. So there's going to be a middle ground how slow you can go with your gradient. In this case, I would say this C gradient, the 15 to 55% B in 30 minutes, give really the good separation and also good runtime as well. Okay, we did a lot of studies with lithium chloride gradient, sodium acetate lithium chloride. This is at a pH 5. When we ran at a 0.8% B per minute, we got this separation profile. And if you want to further improve with changing the gradient, so we reduced to 0.38% B per minute. We can see these peaks got pulled apart, and also it came out later because we have the same starting buffer B concentration. So ionic strength. So with a slower gradient, we get a later elution and also get a dilution of the peaks as well. This is the Proteomix in-SCX pH and salt gradient. As you can see, with 1% B per minute, we get a really already pretty good separations. You can see all this. If we want to see the effect of the gradient, we slow down to 0.7% B per minute. We do get a better resolution among these peaks. You can see more of the baseline separation with these peaks. Also, it came out earlier also because we increased the concentration of B to 5 instead of a 0 here. So with higher ionic strength, we get a peak eluted earlier than the this gradient. All right, so now we move on to the flow rate. General thinking is really increasing flow rate will reduce the runtime, but you cannot really increase, you know, forever. You have to consider the column back pressures and also the resolution, because the resolution is the key here as well. So there's going to be a balance between speed and resolution. This is a very good example on increasing the flow rate and then the impact on the separation and the shortened runtime. With Proteomix in-SCX MP5 with the pH and the salt gradient running at a 0.8 ml per minute, with this map we get a really good separation, and with a back pressure and 105 bar. Proteomix in-SCX can withstand much higher pressure, so that really gives us the room to increase the flow rate and to reduce the runtime with the same column. So we decided to switch to 1.5 ml per minute. It runs at 180 bar, still well below the limit. We maintaining the gradient means we maintain how much buffer going through the column. So the column volume of the buffer is the same. As you can see, the overlay here, we do get almost identical profile. With this example, is really due to the low pressure of the Proteomix in-SCX, we can achieve much faster analysis and high resolution with the higher flow rate. But however, you have to look at the sample and buffer system. Not every sample can achieve the same thing. You have to do a lot of modifications. With next example, it's another different map with a phosphate buffer system pH 7.5 on the same SCX column. At a 0.8 ml per minute, we do get a very nice separation of a 3 nicely separate, and with some other variance here. When we increase to 1.5 ml per minute, these two peaks start to merge. However, we did not try any intermediate flow rates. So if you try 1.0 ml per minute or 1.2 ml per minute, that may already give you the satisfactory results and also reduce the runtime to a certain degree. But under these two, almost cutting in half runtime, it did not work out for these two. So you will have to do some of the method development, try different flow rates, and to see the effect of the resolution and the runtime. Now we'll move on to the column temperature. Column temperature has actually effect on the viscosity of the mobile phase, so that will impact your separation. And also, it will impact on the protein structure as well. You have to, when you do different column temperature, you really have to think whether your protein or the map is stable under the temperatures you will try. A lot of fusion proteins actually have wide range of the temperature stability, so you can definitely try different temperature. Here we just want to illustrate the effect of the column temperature on the separation. This is a map at 30 degree and 40 degree. As we can see, when we increase to 40 degree, only this section has slight improvement, but however, in these areas get less of the separation. So in this case, I would say 30 degree will be optimum for this map. And I have to mention, most of the map separation in this webinar, we use actually 25 or 30 degrees. So we did not go much higher. But for, in general, when you do the protein separation, really the column temperature, you have to take that into effect to see if you can change this parameter to improve the separation. Okay, so we talk about all the variables, and this one is going to be the particle size. All the same column chemistry, but the different particle sizes for the cation exchange. The smaller particle size, the better the resolution under the same column dimension with the same method. A lot of times when you go down the particle size, you actually can cut short the column size and then achieve the same resolution. But for comparison reasons in this webinar, we actually talk about the same column size but a different particle, same column size dimension but with different particle sizes. This is the AntibodixTM WCX, MP10, and then MP5 comparison with the lithium chloride sodium acetate gradient. It's beautifully run on the MP5 in comparison to MP10. MP5 achieves much better resolution with a smaller particle size. And these are all run under the same buffer gradient and with the same buffer system. Another comparison are WCX with a different map, with also a different buffer system with a sodium phosphate buffer system, salt gradient here. First glance, you can see we do get a much better resolution in this range here with the same gradient. Zooming into the area, with all the circled area, it's very obvious. With smaller particle size, 5 micron, we achieve much better resolution with all these variants. So smaller particle size will give you better resolution. But a lot of times when you have 5 micron, 10 micron, if you already have a satisfactory results, so that'd be fine. If you want to achieve higher, you may try lower the particle size. We also get some questions during our tech session. Some customer will ask, is my current map will behave the same on the same column under the same buffer system as my last map? It's really due to different map design and the different production cycles. You will introduce different heterogeneity of the map into the sample. So definitely they will show some differences, but you may have some similarities if you have a same class of map there. Here's an example I want to show you is with two very different maps run under the same column and the same buffer system, even with the same gradient. We do see two complete variant profile, and with a map to PI at a 9.0, we get 3 distinctive peaks with some smaller peaks at the front, and with a map 321 PI at 8.5, we do see a very different profile. So we cannot say they're going to be the same if you have same column, same buffer system. So they will exhibit different profiles. So on the market, there are already a lot of cation exchange for the map separations. We want to compare our column to some other columns on market and to see what kind, the different surface chemistry and what kind of effect on the separation. Here's a comparison between Proteomix SCX and P5 versus a competitor SCX using a pH salt gradient with this specific map. With the overlay, we can see the competitor's column perform better, where the red circle here, you can see there's a split for this peak. Once you zoom into this area, next slide's here, we can see first thing, here's better with the competitor's column, and also if you look at the zooming area, the Sepax column SCX has much better separation in this area here. So with different surface chemistry, of course, from different vendor, you get a different surface chemistry, then you'll have a different separation using the same methods. So optimization is really the key when you compare two columns. They may not lead to the same results under the same condition. This is a comparison with a different map using the same set of column, the Proteomix SCX versus the competitor's column, also SCX. With our SCX, the map 1-6 separates all the three major peaks with variance in the front. However, with competitor's column, we can see most of the protein, the map came out earlier in the gradient, did not really separate on the column. I really want to emphasize this when you compare columns. You really have to optimize the conditions for each column. In this case, we did not optimize any conditions for the competitor's column. We have used optimized condition from our column and run both. So when you do really do the column screening, vice versa, if you have our column or have a competitor's column, when you want to use the other column, it's definitely worthwhile to optimize the condition and to see if you can get a better resolution. So in this case, under the same condition, Proteomix SCX perform better. Also on the market, also a lot of customers using WCX, and then they are looking for some alternative columns for their study, for the map variance study. I have the analysis WCX and the SCX here, so it may not be like a head-to-head column phase comparison. I just want to give everybody a choice. You also can use strong cation exchange to do map separation. In this case here, Sepax SCX performs better in this region. Actually, you get a much better peak here. You can integrate it actually easier than the competitors called WCX. Okay, so how do we compare the WCX and then our antibiotics WCX and the vendors WCX? This is the same map 321 using the sodium acetate and the lithium chloride. As you can see, we do get good separation when we put competitors column under the same condition. We do see some separation. However, most of the map did not get a retain on the column. It came out in the 10-minute flow through. So further modification for this column will be needed if you want to improve the resolution, but we don't know if we can get to the same resolution as our ABX WCX. So when you evaluate the column, do try a few rounds, optimize the conditions on all the columns you're going to screen. So you're going to compare the best conditions for each of those columns, even with the same buffer system. Okay. So we have talked about the particle sizes and also this column comparison. We're going to do next. We're going to do a case study. Just with an antibody, we only know the molecular weight, but we don't have know the other information from our collaborator. Even though the PI is unknown, you actually can run the IEF, but we left it as that. So we're going to screen our cation exchange phases, and also with different running conditions, the pH, the buffer systems. We're using the pH 5.15 with the sodium acetate buffer, and also the phosphate buffer with a pH 7.5. I will also go into a pH gradient, pH salt gradient. We did it with the MAP 321, the pH 6 to pH 10.5 with the salts in the B. And also there's a Hibis buffer 8.0. We added another buffer system, tris buffer, which is really suitable for the anion exchange. At a pH 8.2, it is slightly positive charged. So it will participate a little bit into the binding and the elution there. So we will see the effect of this just tris buffer on the separation of this specific map. You don't have to write on all this. We'll send everybody a slide deck with all the conditions, so you can take a look at it in detail later. Antibiotics, we tried antibiotics MP5 first with all these 5 buffer system with the lithium chloride pH 5.15. It has some separation, but not very well defined peaks. Here just some shorter, and with the phosphate buffer, it's actually not too bad. It elutes early though, and also it has some separations between the peaks. Interestingly, with pH salt and the tris buffer, it gives us a similar kind of profile, but in different regions have a different resolution. Hibis buffer 8.0 is similar to the phosphate. You get 2 areas with the peak separation, but you get a much better resolution. So with the slight difference between tris and the pH and salt, I really think there's a common thread here, because the pH salt also has the buffer ingredient, the tris in the pH and salt. Proteomix SCX MP5 with the 3 buffer system, lithium chloride didn't do the job at all. It just come out as all the broad peak. And the phosphate did a little bit separation, but not as good as the WCX. The pH and salt and the tris buffer similar to WCX. It has different selectivity, the different resolution between the peaks. And then the Hibis buffer as well, you do see the separations between those peaks. And then the peak area, these patterns are very different from the amine-based buffers. Proteomix WCX, so I'll have the overlays on each phase with the buffer as well. Unfortunately, we did not have enough samples to screen all 5 buffers on the Proteomix WCX. We did 3 buffer systems. Among all 3, while the Proteomix WCX did not outperform the Proteomix SCX or Antibiotics WCX, but just compare the 3 buffer system, you can see the pH and salt gives a little bit of advantage for the separation. The pH and salt gradient overlays, we can see the Proteomix SCX and ABX has a better performance than the Proteomix WCX. ABX has better separation in this range maybe, and also the Proteomix SCX forms better than the ABX WCX in here, where my red circle is moving here. So that's the pH and salt gradient. And we'll move on to the ABX WCX MP5 and SCX MP5 with a tris buffer. That gives it a similar pattern, but however the resolution, there is some difference in the resolution. The antibiotic is better separation in this range, basic region, and then also the Proteomix SCX has a better separation in the acidic region here. So the Hibis buffer at the pH 8.0, ABX definitely has a better separation in these later peaks, and then the SCX has slight advantage in the front end of the peak here. So in the end, actually, our collaborator settled on the tris buffer system using Antibiotics WCX MP5 for their antibody lot-to-lot test. We have tried a 3 lot of material on this column with this tris gradient. We can see lot 1 and 2 are very similar with the charge variance separation here. And the 3, there are quite a few peaks disappeared. Later we learned from our collaborator the difference among the 3 lots of antibody, 1 and 2 were manufactured in the same year and from the same growth method. The antibody 3 actually is manufactured another year. The cells were harvested at a different growth week. So that's actually explained the map heterogeneity. Some of them removed from here. So we have talked about a lot of methods, a lot of buffer systems used on our ABX and SCX. Next, we want to talk about monoclonal antibody applications. We use those methods for the monoclonal antibody separation. First, we'll talk about map stability. A lot of times people already use size exclusion for the aggregates and the monomers and the fragmentation studies. Here we want to use cation exchange to see what kind of profile we have. Also the deglycosylation. After removing the glycosylation, what happened to the map and what kind of profile we'll get. The next we'll talk about a carboxypeptidase B digestion. So carboxypeptidase B will remove the C-terminus lysine, and after the carboxypeptidase digestion, what kind of map profile we'll see. So this is the first I want to just show you the SEC analysis of this particular map. One is a fresh and the other one is a highly aggregated monoclonal antibody. At the 17 mg/ml, identical concentration. You can see the fresh sample has, you barely can see any of the aggregates, but with a highly aggregated monoclonal antibody, you can see the dimers and a high order of aggregates. So that we can see from the SEC. So if we apply these two samples on the cation exchange, what kind of profile we'll have? That's what we're going to show next. Aggregated map separation, they look very identical in this region where the monomer comes out with the different variants here. This is using a 20 millimolar Hippies buffer with AntibodixTM. However, due to a highly aggregated map sample, they have much higher net positive charge, so the aggregates retain on the column much longer, so they eluting in the later salt concentration. This is another stability test we did on the cation exchange. We want to see this map stability because we use this map a lot, and we don't want to freeze and thaw all the time with the same tube. So we want to see how stable it is in our autosampler. We did a 2-week time frame. This is the overlay of freshly defrosted sample and 1 week and 2 week. As you can see, all these maps coming out showing the very identical variance peaks. So for this map, it's very stable at for 2 weeks at a 4 degree. A lot of maps are kind of stable at a 4 degree for a long time. Deglycosylation. So a lot of people deglycosylate a map and study the glycosylation here. We just want to see what kind of variance profile we get for this map after removing the glycosylation. There's no peak for the enzyme control here, and for deglycosylated the B trace here in comparison to the intact map, we can see all the peaks were shifted earlier. This we used a CEX MP5 and the pH salt gradient. We think the shift is really due to the removing of the glycosylation. The asparagine got converted to aspartic acid, so you introduce more acidic species. It came out earlier than the intact map. And then the carboxypeptidase B digestion. This is for this specific map 321. We didn't know a whole lot about this map. When you overlay the digested and then the intact map, you didn't really cannot tell much of the difference here. But once you move down to the zooming area, there are some differences you can see here. The peaks disappeared, getting smaller. So these are the indicating of the lysine variants. For this particular map, the percentage of these variants are kind of small. So for all the other peaks, further analysis is needed to really determine what are the heterogeneity for this particular map. Okay. All right, so we talk about the column screening, we talk about the applications, and we talked about earlier the variables go into the method development of the map separation. So our conclusion will really, we did all these method development and also showing you the optimized salt and pH gradient or combination of those gradients using our antibiotics WCX and then the Proteomix CEX column for the map separation. Actually, we have an IEX screening kit including the antibiotics WCX and the Proteomix SCX for you to screen the samples and also to find out optimized conditions for the map separation. All the methods we have talked about here actually can really not only apply to the monoclonal antibody, can be applied to any proteins and all the following sample types: the map fragments, the Fab and FC, and also the Fab2, and the biosimilars. Not only the monoclonal antibody biosimilars, you also can have the other protein biosimilars drugs as well. ADC has become a very important drug category. So they will run very differently from your naked map because sometimes they have the lysine conjugates with a small molecule attached that you lose all the charges on the lysine. And also sometimes the small molecules will change the entire molecule, the structure, so that will give you the different charge variants as well. Fusion proteins, there are also a lot of people working on fusion or different kind of fusion proteins. For fusion proteins, they do actually have a wide range of PI. If you have a PI of 5 or 6, you actually also can try anion exchange column SCX or WX to see if you have a different selectivity and get a more improved resolution. Pegylated proteins being also a very big categories of the sample types. Due to the pegylation, protein structure will change and also will affect all the charges on the surface where it can bind to the resin. So all the methodology we have talked about can be applied really actually to all the protein separation. And the separation is really time consuming and also takes a lot of resources as well. So if you can follow these steps, I think you can get a faster method development. And of course, we also offer actually a method development service. If we are willing to send us some samples, we can screen the column phases and also the buffer system for the initial screening for your research as well. Okay, so we have talked about ion exchangers, the proteomics antibiotics. We also provide size exclusion columns for the protein size differences analysis. If you have any questions, please do not hesitate to contact us, and we are here. Also, the method development service also include SEC screening as well. So that concludes our webinar. Thank you very much for attending. We'll move on to the Q&A session. And here are our contact information. So if you have any questions after our webinar, you can give us an email, give us a call, and you can contact me personally as well. So we'll try our best to help you for your research. Okay, here are some questions. All right, let me read it. Can you use ammonium as the cation exchanger instead of a sodium or lithium? Ammonia, actually, the answer will be it's ammonium-based mobile phase is actually a very common choice for volatile mobile phases. We actually have some data to show using the ammonium acetate or ammonium formate in the mobile phase for a lot of times a volatile buffer for the SCX or CEX for the mass spec study. So yes, you can. Okay, second question. You mentioned the benefit of the reduced viscosity in the mobile phase at a higher temperature. In reverse phase, the higher temperature helps a lot with higher diffusion coefficient. Does that also help in IEX? The answer, okay, yes. At higher temperatures, we can sometimes see sharper peaks, but it's really important to know your sample. And also need to know, how high the temperature will affect your sample. Some of the samples at the even 40-degree will denature, precipitate out of the solution. So really have to see the stability of your sample. I mean, of course, the temperature will affect protein structure. So that's all related. Okay, so there's another question. Why you're seeing different peak intensities when you have different gradients? actually peak intensity is normal when you have different gradient when you run. All really important is the peak areas. So the peak areas will be consistent if you integrate them. But for the peak height, you will see the different peak height for some under different conditions. Is competitors, okay, another question, is competitors column you mentioned optimized when you do the comparison? No, with all the study we have, we optimized conditions on the Sepax column, and we apply the same column for these competitors column. So really I have to emphasize, when you compare the columns from different vendors, it would be great if you have similar results or get a one over another one. But if you have a really drastic different profile, I would really suggest you optimize the conditions for both columns or one of the columns, and then compare the resolution. So due to the surface chemistry difference, you will see the difference there. All right, one more question. What is the lifetime of the Sepax cation exchange column? For our columns, we have tested with the QC methods up to 250 runs. We get a lot of times the customer feedback. They actually can run 500, 800 runs. But I have to emphasize, it's all depending how you take care of your column, whether you have a guard column, pre-column filter, storage conditions. So really you have to make sure the whole process is smooth, and then also the cleaning of the column. So these are very important factors go into a long column lifetime. Okay. All right, that's all the questions I have. And if you have more questions, please contact us. Anytime. We are here to help. We have a technical group, so you can send us an email or phone calls and let us know, and we'll help you further research or help you, every step of the way. I want to thank everyone for your time, and thanks for joining our webinar today. All right. Hope everyone have a good Thanksgiving. Bye.